So you take an object like that and you rotate it. That would be something that's useful, you can imagine, in computer graphics. But how are you going to do this? Now, one of the neatest ways of doing this mathematically uses a new type of number beyond the regular numbers you know. So there's beyond the real numbers, as we call them. They're even beyond the complex numbers. If you've heard of complex numbers before, it's even beyond that. They're called quaternions. They're fantastic. So imagine I want to move along in one dimension. So you're living somewhere here. And if I said move +5. +5 means you move 5 units to the right along this line. So I'd end up over here. If I said instead move -3, you might understand that means move 3 units, but that time move 3 units to the left. So that's how you move in one dimension. That's fairly easy, isn't it? All right, let's talk about moving around in 2 dimensions. And let's say I want to end up at a point over here. What that might be, 3 units this way, let's call that a 3. And then I move 4 units up. Like that. One way you could write that as a set of instructions is to write it as 3 + 4i. Some of you may know what's coming here. Some of you may have seen this I before. But for now, let's just say I means turn 90 degrees and go up and down. Right, for now, that's what it means. Right? So that's one way I could travel to that point. Or alternatively, I could look at it this way. I could travel 3 across and 4 up. Or I could rotate myself to this angle here and move along this diagonal line here. And that would be 3 + 4i as well. Right? You could use the same instructions to make that point. That's how you travel in 2 dimensions. I mean, if I want to then go further and travel maybe a bit more further on, so let's say I wanted to go maybe 1 more across and then 2 up, like that. What I could do then, by adding a further 1 + 2i, I end up at this point. And I can say that this point is the combined result. Which means I've actually travelled, what, 3 across and then a further 1, 4 across and 6 up. Or, if you like, it's the combined result of going from here up to here. So we can add these numbers together, and we should think of them as numbers. Right? You can add them together, and you can move around in 2 dimensions. So this time, let's rotate this line. Let's take my combined result here. What have I got? This is 4 + 6i. Let's rotate this 90 degrees. If I rotate it 90 degrees, I think it's going to end up something like that. And it will end up here. It will end up on a point here. So this is going to be a 90-degree rotation. This point is actually -6 + 4i. And that's where I end up if I rotate. These look similar to each other. Why do they look similar? How can I get from this number to this number? What I've done actually is I've multiplied. Instead of adding the numbers together, I've actually multiplied this time by the number, we call it a number, the number I. So there is a special rule with this. The special rule is I times itself, I times I, is equal to -1. Just to show you what I did, I took where I was, 4 + 6i, I multiplied it by I, and what did I get? I got 4i plus 6, well, let's call it I squared. Oh, what is that? That is 4i minus 6, yeah. Or in other words, where I ended up here, minus 6 plus 4i. So multiplying by that number I means you rotate 90 degrees. If you do it twice, you get -1, which does make sense. So if you rotate 90 degrees and then rotate 90 degrees again, you're 180 degrees now, you're facing the opposite direction, so you're going negative direction, so it does make sense. And it turns out that if you multiply these numbers together, you get rotations. When you multiply the 2 numbers together, you add their angles together. So if I want to rotate 45 degrees, I would get my triangle for 45 degrees. 1 over root 2 there, 1 over root 2 here. So that's nice, and that's a 1 now. That is a 45-degree angle. Written as a number, that is 1 over root 2 plus 1 over root 2, lots of I. There you go. So I've gone that distance across and then that distance up. If I multiply by that number, I would rotate by 45 degrees. So adding them together makes you travel around in 2 dimensions. Multiplying them together makes you rotate in 2 dimensions. Now, if you're ahead of me and if you've seen this sort of thing before, you may recognize these as complex numbers, which, by the way, is a terrible name. Complex numbers, which makes them sound like difficult numbers, which I don't think is the intention. I think the idea is they are compound numbers. They are actually 2-dimensional numbers. That's a way of thinking of complex numbers. Real numbers are 1-dimensional numbers. Complex numbers are 2-dimensional numbers, and you can use them to travel in 2D and rotate in 2D. So the question is, how do we rotate in 3D? We must need 3-dimensional numbers, right? So we must have to introduce an I and a J as well. So we have 3-dimensional numbers, and that's what people thought. It turns out we don't need 3-dimensional numbers. We need 4-dimensional numbers. To rotate in 3 dimensions, bizarrely, you need a 4-dimensional number. Let me show you how this works. So right. So there was an Irish mathematician called William Hamilton, and he was thinking about this problem, and he couldn't solve it. He said, it doesn't work in 3 dimensions. I can't get it to work. And the story goes that he was having a walk with his wife along the canal in Dublin, and then suddenly inspiration struck, and he suddenly realised, I don't need 3 dimensions. I need 4-dimensional numbers. I need I, J, and K. So flushed with this, he immediately walked over to a nearby bridge over the canal, and he carved in the rules that he needed to make this work. These are the rules that he carved into that bridge. I squared is equal to the J squared, which is equal to the K squared, which is equal to I times J times K, which is equal to -1. It's very similar to the complex number idea. The complex numbers, I squared equals -1. That's what we needed for that. It's very similar, but no, we need I, J, and K. He carved this into the canal bridge, which unfortunately, graffiti, what a vandal. Unfortunately, it's not there anymore, but now there is a plaque celebrating the rules, or his discovery of quaternions. The rules are there, and every year, mathematicians around Dublin have a pilgrimage to the spot where he had this idea for quaternions for the first time. So by multiplying these 4-dimensional numbers, you can now rotate, like the 2D version, you can rotate things in 3 dimensions, and this is how things are done using computer graphics. But not only that, it's how things are worked out for the rotation or the orientation of a space shuttle going up, or it's how they work out the orientation or the rotation of your smartphone. So let's say I want to rotate an object in 3 dimensions. What I do is I pick a line like this pen here. I stab the object with this pen, and then I can rotate around this pen here. So I might stab it this way, and then I can rotate the object like that, or I might stab this way, so it rotates the object this way, or else this way, and so we can rotate like that. So how do we write this? So I take a line like that, and then I want to rotate around that line. Let's do an angle of theta like that. Let's call it V. This line we're calling V. So it's a 3-dimensional thing. It has 3 coordinates. So let's call it V1 and V2 and V3. Let's take a point that's getting rotated around. So let's call that a P. And that's just X, Y, and Z for that point in 3 dimensions. This is how things work. But now we're going to rotate it using a quaternion. What does a quaternion look like? It looks like this. A quaternion, let's call it H, would be something like A plus BI plus CJ plus DK. And actually for this, I do need another little thing, something called H star. And H star is A minus BI minus CJ minus DK. Right. If I want to rotate by an angle of theta, A, B, and C are defined as A is going to be equal to cos of theta over 2. B is going to be written as v1, that's come from my vector here, that my stabbing pen, sine of theta over 2. The c is v2, lots of sine theta over 2. And the d needs v3, lots of sine theta over 2. So it turns out we need 4 components for our number that we're going to use. We need 4 components to have the freedom to do the stabbing and then the rotating around that vector. And how do you work out the rotation? And then finally, if p, which is the point I'm rotating, you write p as a quaternion. Its coordinates are x, y, and z. It's actually x, lots of I, plus y, lots of j, plus z, lots of k. And finally, the rotation is h, p, h star. Right, that's the maths of it, right? That's the main maths. But we need 4 components to our number to have the freedom to be able to rotate around a vector and then move the angle around it. So the complex numbers contain the real numbers as well. And it turns out the quaternions contain the complex numbers, and in turn, they contain the real numbers. And when you don't need the j and the k, now you've got a complex number, and if you don't need the I, you've got a real number. So you might be thinking, what's next? Is there a next step up? And there is. The next step up is octonions. 8-dimensional numbers. Octonions, which have their own set of rules as well, very similar, but a very similar idea, but every time we go a step further, they get a bit more abstract. They lose a bit of structure, and there's a property that you lose each time you do it. So the more you do this, the less useful they become. Octonions have some uses in very abstract maths, but they're not as useful as quaternions are. And there is then a step above that, the 16-dimensional numbers, the sedenions. But again, you lose another property when you go further. And each time you do, they get perhaps less useful. Unfortunately, what you lose is when you go from the complex numbers to the quaternions, the property you lose is this. In complex numbers, a times b is equal to b times a. So the order doesn't matter when you multiply numbers. So 3 times 5 is 5 times 3. In the quaternions, that's not true. Order does matter. And that makes sense using this 3D rotation as well, because if we're taking our rotations around an object, then order does matter. If you rotate one way and then rotate another way, it doesn't matter which order, you do get a different answer if you do it in a different order.
Like a Rubik's Cube.
Like a Rubik's Cube. Exactly, he's learning. So many years we've been doing this, he's learning. Yeah, so the order matters. And then if you go one step further into the octonions, what you lose is, typically numbers do this. A times b times c in a bracket is equal to a times b first and then times c. So if I group those and do those first and then do a, or group a and b first and then do c, you get the same answer. Right? And that's true for the real numbers, the complex numbers, and the quaternions, and that's what you lose in the octonions. And then there is a property that's similar but weaker, and then you lose that when you go further into the sedonions. And so each time you do it, everything becomes less structured.